My apologies, I forgot to start the recording, but from now on it's recording. And I will post these not to Canvas, but to YouTube probably, because the tool that UD was using just was not very reliable in the fall. So I'm planning to make the recordings myself and just post them to YouTube so that you can access them there. Okay. So I will try to post lecture notes that go along with what we do in class. Yes. Okay. Let's see. So this. All right. So for the purpose of the recording, remember we started talking about linear algebra. We looked at some strategies for solving. We went through the solution of a simple equation, a simple pair of equations. And we introduced the idea of Gaussian elimination. We're going to go back now and start talking about notation and terminology. Some of you guys have seen this before, in which case it's a reminder, please be patient. But there are always people who haven't seen all of this before. So I want to make sure everyone's on a level playing field. So what's a linear equation? So it's going to be for us something of this form. Okay, so in this equation, the A1, A2, all the way up to the A sub n are coefficients. We want to think of these as known quantities. And these could be real numbers or possibly complex numbers. In general, they could be something, they could be something other than real or complex numbers, but these will cover all the cases that are important for us in Math 305. And the x sub 1, x sub 2, up to the x sub n are the unknowns or the variables. Okay. And we say for this particular equation that this is an equation in n unknowns. Oops, wrong parentheses. Right, because it's a single equation, but we have x1, x2, x3, all the way up to x sub n are the unknown quantities in the equation. So linear means that we don't have sine of x1 or x1 squared. For instance, linear just means that every unknown that appears in the equation appears as itself to the first power. We just have the unknown, not a function of the unknown, other than just the unknown. Okay, so one linear equation in two unknowns could be something like 2x1 plus 3x2 equals 7. Okay, and we could have two linear equations and three unknowns. So x1 plus x2 plus x3 equals 7. 2x1 plus 5x2 plus 7x3 is equal to 8. Okay, so two equations, x1, x2, x3 are the three unknowns. Notice that both of the equations are linear in the unknowns. And if you have, actually, let me change this first equation a little bit. If you have an equation like this, there's some conventions. We can think of a coefficient of 1 is suppressed, right? So x1 is really 1 times x1. x2 is really 1 times x2. x3 doesn't appear, so we can think of that as 0 times x3. Okay, so there are some conventions for simplifying the equations. If you have a coefficient of 1 or 0, right, you just don't write the 1 sometimes, or you just don't write the term if the coefficient is 0. But we don't want to do that when we go to the matrix form of the equations. We actually want to keep track of all these coefficients. Okay, as we'll see later. And this second example we have here is an example of a system. A linear system. Okay. Okay, this is my abbreviation for equations. System, you could talk about a system where you just have one equation, but typically when we say a system of equations, that means you have more than one equation. And a linear system means that all the equations that you're dealing with are linear equations of this type. Now, there's a convention for writing sort of arbitrary linear systems, right? Notice we use these subscripts to distinguish our unknowns rather than using X, Y, Z, W, and so on, because we might have a system where if we had 30 unknowns, right, we're going to run out of letters of the alphabet. So it's easier to pick one letter like X to represent an unknown, and then index X to represent a number of unknowns. So we can write a system. The form A11 x1 plus A12 x2 A1n xn equals B1 A21 x1 plus 22 x2 PM. All right, so notice what I have here. So there are n unknowns. And those happen to be x1, x2, all the way up to x sub n. And there are m equations, right? So there's 1, 2, all the way up to the mth equation is our last equation here. And notice what I did with the coefficients. I used the symbol A to represent a general coefficient, and I'm using a double subscript to indicate which equation the coefficient appears in and which unknown the coefficient goes with. So in the first equation, all the coefficients have a first subscript of 1, right? That first subscript indicates the equation the coefficient belongs to. And the second subscript represents the unknown that the symbol belongs, that the coefficient belongs to, right? So A11, that means first equation, first unknown. So it's multiplied by x1. So something like A sub 47 would mean that we're talking about the fourth equation. And this would be the coefficient of x sub 7. Okay, so is that convention clear to everyone? Any questions there? That looks good. And on the other side, the B's, that single subscript they have represents the equation that the coefficient is associated to. All right, so this is nice because it gives us a convention for writing things. Now we can actually make a matrix out of all of those unknowns. And we can think of these subscripts. Now, again, they're double subscripts. So A sub I, and I'll put a comma in between just to separate the two pieces. That first subscript I represents the row in which that subscript appears in our matrix. J represents the column. In which that coefficient occurs. And notice that the row here looks like it goes along with our first equation, right? A sub 1 whatever, these are the coefficients in the first equation. So that row coefficient that goes with the ith equation. And the column coefficient that goes with the jth unknown, right? So if your second subscript is j, that coefficient is being multiplied by x sub j, the unknown x sub j. And this is a matrix. A matrix is just a rectangular array of coefficients. Of numbers or scalars. It doesn't have to have the same number of rows or columns necessarily. It just has to be rectangular. And this matrix that I've written down is called the coefficient matrix for that system that we had over here. All of the coefficients on the left-hand side of the equation are put into this matrix. So this is our coefficient matrix. Written on the previous page. Now, we had our unknowns, so we can put those together into a column matrix, or a column vector, I should say. Right, this is a special type of matrix, but we'll typically think of this as a distinct thing called a vector. And we also had this column vector of coefficients on the right-hand side of the equations. So RHS is right-hand side. And notice, if we go back to our system, right, x1, x2 up to x sub n, we've got n entries here. Okay, so we say that this, we can talk about the dimensions of our matrices. Right, we give the number of rows times the number of columns. So for this matrix, we've got m rows and n columns. For this column vector, right, we've got n columns. Sorry, we give rows times columns. So we've got n rows and there's one column. For the b vector here, we have m rows and again, one column. Okay, so we mentioned previously that we could sort of collapse our linear system into a very compact representation. And to understand how this works, we have to understand how matrix multiplication works. All right, so I'm going to try to do this just by writing out actually, let me do this. All right, so here's an example of a matrix. This is our matrix A, say, times a column vector unknown. Let's call it X underline. Now, what are the dimensions of this matrix A? We have 2 rows and 3 columns. What are the dimensions of this column vector X here? Well, we have 3 rows and we have 1 column. So matrix times vector multiplication is a special case of matrix times matrix multiplication. And the way this works is you always go along the rows of the first matrix down the columns of the second matrix. You can check whether the product of two matrices is actually defined by thinking about the dimensions of your matrix, your matrices, and making sure that these inner numbers agree with each other. So if I go across the row of the first matrix, 1, 2, 3, I need to multiply 3 separate things. So each of these is going to hit something in my second matrix. So there has to be 3 things to hit. So the 1 hits the X, the 2 hits the Y, the 3 hits the Z. Okay. And the dimensions of the product, when you multiply a matrix times a matrix, those are coming from these outer indices. So I should get a 2 by 1 matrix. So that's going to be a column vector with 2 rows and 1 column. Okay. And in position I comma j in your product, you use the ith row from your left matrix, the jth column from your second matrix. So here, I'm going to have 2 entries in my results. We saw how to go across the first row down the column. Now we go across the second row, 4x plus 5y plus 6z. And that's our results. And let me just get rid of the dots there. So x plus 2y plus 3z. All right, so sort of by example, showed how to multiply 2 matrices together. This multiplication has lots of properties that are important to be aware of. And probably the most important thing to be aware of is that this is not commutative. Okay, so what's commutative mean? Well, order matters. If I have a matrix A times a matrix B, it's not necessarily equal to matrix B times matrix A. In fact, one of these products might be defined and the other one is not defined. So for instance, let me take my matrix A to be 1, 2, and my matrix, was there a question? Okay, and my matrix B to be something that looks similar. So let's see what happens if I reverse the order with these guys. And let's practice. So what are the dimensions of this first matrix? This is called a row vector, right? It's really just a row of a matrix. So there's 1 row and 2 columns. The second guy, that's a column matrix. It's got 2 rows and 1 column. So notice that both of these products are defined. The inner indices match up. But even though they're both defined, they're not even matrices with the same size. So on the left, I'm going to wind up with a 1 by 1 matrix. The result is going to be 1 times 1 plus 2 times 2, or 5. And notice what I get on the right-hand side. The result's got to be a 2 by 2 matrix. So I go across the row down the columns. I get 1 times 1 is 1, 1 times 2 is 2. And then for the second row of my product, I go across and down. 2 times 1 is 2, 2 times 2 is 4. Okay, so A times B is defined, B times A is defined, but they're not equal to each other, and they're not even matrices of the same dimension. So if I do 1, 2, right, that's one row times 2 columns. And let's say I have a 2 by 2 matrix, Wx, y, oops, Wx, y, z. If I try to reverse the order, notice what happens. This is a 2 by 2. This is a 1 by 2. And this product is defined. The second product is not defined. So that result is going to be a 1 by 2 matrix. And this guy is not even defined. Okay, well, let me ask you guys a question. When will A be and B A? So the two products of our matrices have the same dimensions.
When they're squares.
Exactly. Good, good, good. And what that means is they have the same number of rows and columns. Okay, so if you think about it, we have I times j for a matrix of dimensions I times j to be multiplied with a second matrix. The first index has to be j. These guys have to match. And if we reverse the order, oops, j times k times a matrix with dimensions I by j, well, k's got to be I for this to even be defined. And the result is j by j. Well, what about the first guy? That result is going to be I by k. So k is equal to I, so this is I by I. And if I want these to match, then I is going to be equal to j, or in other words, the number of rows has to equal the number of columns, in which case we say our matrix is square. Okay, well, if your matrices are square, is AB the same as BA? Okay, so what do you think? At least both of these products are going to be defined. They'll have the same size. Do you think they have to be the same thing? Okay, so somebody in the chat says no. Several people say no, and the answer is no. Okay, it's very easy to come up with examples where A times B, B times A are not the same. Okay, and I encourage you to try to do that. Okay, so let's see. So can anyone come up with an example of, let's say, 2 by 2 matrices? Where this happens? I'll give you a minute to think about that. Any ideas? Anyone want to take a guess?
How about this? 1100, then second matrix is the 1010.
Oops. So is that what you meant?
Yeah.
All right, so let's check. So if we go across and down, we're going to get 2, 1 times 1 plus 1 times 1. And then we're going to get 0. And then we're going to get 0, 0. So let's change the order. Let's see what we get this time. So if we go across and down, 1 times 1 plus 0 times 0 is 1. Already we know they're going to be different. So 1 and 0 is 1. 1 and 0 is 1. 1 and 0 is 1. Very good. Thanks for giving me an example. Okay, so here's an example of this phenomenon. Now, it's kind of complicated in general to come up with a set of conditions that will tell you when the order doesn't matter when you're multiplying two matrices. So that may be true for some matrices. Right. The point is that it's not guaranteed to be true. You can come up with examples where it doesn't happen. It's kind of complicated in general to come up with the conditions that guarantees that A times B is the same as B times A. There is a simple situation where commutativity is guaranteed. And that's when your matrices are the same. So if I have A times A and I switch the order, I still have A times A. So but more generally, if I have powers of matrices, right, those are well defined. Okay, so if I want the third power of the matrix, it really doesn't matter how I break down computing that. It doesn't matter because however I try to build up to A cubed, I'm guaranteed to get the same result. Okay, and one last thing. For today, at least. If the indices of your matrices are such that this product A times B times C is well defined, then it doesn't matter how you group when you're computing this product. Okay, notice I'm not reordering anything. I'm just either computing B times C first and then A times that result, or A times B first and then that result times the matrix C. So the matrix product is associative, right? It has this property, but it's not commutative. And notice, if the matrix A is, let's say, I by J, the matrix B has got to be J by K, the matrix C is K by L. If I look at this result, it's well defined. So B times C is defined because the K's are the same there, the inner indices. And that result is going to be J by L. Now the J and the J match up. So A times that product B times C is well defined. And the result is going to be I by L. If I do it the other order, or if I group in the other way, I should say. So if I group the first pair, the J's match, so those inner indices match, that result is going to be I times K, I by K. Now the K's match, so that result is well defined. And notice my result is going to be I by L again. All right, so I think that's where we're going to stop for today. So thank you for your attention. I can hang around for a couple of minutes if anyone has questions. But I have another meeting at 11, so today I can't hang around for too long. So thank you for coming to class. I hope this was useful, and let me know how things are going as we move forward. Okay, have a good day, everyone.
Go on.
Thank you.
Thank you.
Thank you. But I have a question.
Sure, go ahead.
So look like this class is a combination of the It's a combination of the linear algebra and the differential equation, right?
We're studying some parts of linear algebra. We're studying differential equations. Yes.
But I already take a differential equation with 302, and I have a credit for the linear algebra, which is the, let me check right now.
Is that 349?
Yes, 349 elementary linear algebra.
Okay.
So could I substitute?
So what is your major, Chi? What is your
Excuse me, you are
major?
lagging. Oh,
Oh.
Chem E.
Your chemical engineering. So you would need to talk to your advisor in chemical engineering.
Yeah.
I don't know exactly what their rules are, but if you've already taken 302 and 349, I think there's a reasonable chance you could use that to substitute for 305.
I got it. Thank you so much. And I'm gonna contact her today.
Okay, that's fine.
Yeah, because she only says 302 is not substitute of the 305. I totally agree because 302 is just DEQ. But
Well,
I have
the reason they
algebra.
might not allow that is because of the MATLAB component in 305.
Okay,
So,
okay.
so then the
I gotta
question,
talk
do you
with.
have any MATLAB that you could argue is covering that part of it?
Okay, so I did pretty good job in the comp sci. I'm just gonna argue with them. Okay, thank you.
Yeah, I can't do, I can't tell you the answer there because I'm not I'm not in the chemical engineering department.
Hey, got it. Thank you so much.
You're welcome.
Have a nice day.
You too.
Hey, I just had a quick question. Could you briefly go over the matrix multiplication?
Briefly go over matrix multiplication. Okay. Just the basic definition you're saying?
Yes, just like I know you mentioned you like multiply across and down, and I do want to real quick.
All right, so I can do that. Does anyone else have a question they need to ask? That's going to be quick.
I have a quick question. So last semester I took 243 and I'm in chemistry. So this semester I'm supposed to take 305. Do I need to take any prior class to 305 or 243 can get to 305?
The prerequisite is 243 and CISC 106, I believe.
Yes, I took those class. And now do we need to take any more class to understand and then take the 305, or I can currently stick 305?
You should be fine if you've taken the prerequisites.
Okay. Can you please post the lecture note onto Canvas because you skipped to another pretty quick. Some part I didn't have a chance to write down. Thank you.
Okay.
I have the same question as Chris does. But also where do we find the textbook?
I'll give you a note from the Canvas, a link from the Canvas page.
Okay.
All right, so matrix multiplication you guys want to see, right?
Yes, sir.
All right, give me a second here. Actually. So this first matrix here is 2 by 2, second is 2 by 2. The product should be 2 by 2, right? 2 by 2 matches. The outer indices are telling you your product is going to be 2 by 2. So if you go across the rows down the columns, in the 1, 1 entry of your product, first row, first column, right? You're using the first row from your left matrix, the first column from your second matrix. That's going to be A times W plus B times Y. How about the 1, 2 entry? in your product? Well, first index is 1. So again, you're using the first row of the first matrix here. Second entry is 2. So you're using the second column of your second matrix. If you go across and down, you have A times X plus B times Z. Okay, same thing in the second row of your results. CW plus DY. And then for the 2, 2 entry, second row, second column, you use the second row, second column, C times X plus D times Z. All right, that's the basic idea. If your matrices are of different dimensions, you just use that idea appropriately. So is this particular problem clear?
Yeah, that's perfect. Thank you.
Okay,
Yes, it's clear.
good. Is that enough?
Yes.
All right,
I'll see you next class. Thank you.
see you soon.
All right.
Bye, guys.